Welcome. This video is going to go over the ideas introduced in Chapter 2, Section 1 of the Brown SL Chemistry book. And in Chapter 2, they start talking about atomic structure. So Section 1 is going to be a quick review of a lot of things we've covered before in chemistry, specifically what the atomic structure looks like, the 3 subatomic particles, and how scientists came to believe that this is what atoms look like, and also how this has led to the discovery of things such as isotopes and ions. So the quote, "all things are made from atoms," is considered one of the most important ideas we've ever uncovered. And it started its origins back in Greek and Indian philosophy nearly 2,500 years ago, but it took until the 19th century or the 1800s to have any experimental evidence to support the idea. And today we actually need this quantum theory or quantum mechanics and a wave description of matter to actually be able to understand or explain elements' behavior. So Dalton's model back in the 1800s was really the first to start explaining in greater detail what atoms might be like. And he had noticed that hydrogen and oxygen always combined together in fixed proportions, which eventually led to the law of definite proportions. And he was the first person to assign chemical symbols to different elements. And he explained the behavior of hydrogen and oxygen he was seeing by proposing that all matter is composed of tiny, indivisible particles called atoms. He also said these atoms cannot be created or destroyed. Atoms of the same element are alike in every way, but atoms of different elements are different, whereas atoms can combine in different ways to form molecules. And initially, Dalton's ideas did not get a lot of support, and ironically, Kelvin was one of the scientists who disputed and kind of dismissed Dalton's ideas when he first proposed them. But eventually, his ideas bore out to be pretty much spot on with what we believe about atoms even today. So some of the basic terminology you should know are elements are the substances which cannot be broken down into simpler substances, and there are only 92 natural ones on Earth. An atom is the smallest piece of an element you can have because if you get smaller than an atom, it no longer resembles that element. Compounds are 2 or more elements chemically combined and having different physical and chemical properties than its constituent elements. What that means is when you put sodium and chlorine together, sodium chloride is totally different than either sodium metal or chlorine gases on its own. And molecules form when 2 or more atoms combine, and this may be an element in the case of H2 or O2, the diatomic gases, or it may be a compound such as CO2 or H2O. So subatomic particles. J.J. Thomson was the first one to discover a subatomic particle. He discovered the electron when he was working with metals and passing current through them, and he realized all metals possess these negative pieces, and so he figured electrons are part of all atoms. He also realized that the atom was neutral overall, so he knew there had to be a positive counterpart to balance out this negative electron, and he came up with this plum pudding idea that's a positive atom with negative electrons embedded in it. And since none of us eat plum pudding, I think a chocolate chip cookie idea is a better explanation. You've got the positive cookie embedded with negative chips. Rutherford was trying to prove Thomson's plum pudding idea correct when he was doing his gold foil experiment, where he shot positive alpha particles through gold foil, which is just really, really thin layers of gold atoms. And he was expecting most of the alpha particles would pass straight through, and a few might be deflected by the electrons pulling on the positive alpha particles. But the big surprise was that some alpha particles actually bounced back. So what Rutherford deduced from this is that there has to be a small, dense, positive nucleus instead of this big, massive positive area with the electrons embedded in it. Instead, there's a small, dense, positive nucleus, and most of the atom is actually empty space where the negative electrons are free to move about. We now know the nucleus actually contains neutrons and protons, with the neutrons being neutral. And in fact, if it weren't for the neutrons, the nucleus wouldn't be able to hold together. You cannot pack positively charged protons that tightly together without something in between to give it stability. So protons and neutrons are known together as nucleons. And so the electrons were still the part we were trying to figure out. And Bohr thought the electrons orbited like planets of the solar system. But we now know the electrons move much more randomly in orbits or energy levels around the nucleus, which is what Chapter 2 is going to focus on. A couple other terms that you should be familiar with are atomic number and mass number. Atomic number is represented Z and mass number A, which is kind of confusing, I agree, but you'll just have to commit it to memory. But atomic number is the number of protons, and that's what identifies an atom like fingerprints. If you have 6 protons, it's a carbon atom. If you have 8 protons, it's an oxygen atom. Because atoms are electrically neutral, though, it also identifies the number of electrons if it's a neutral atom. And the mass number is the number of protons and neutrons in an atom, with each a proton and neutron each being given a relative mass of 1. Whereas electrons have such little mass, 0.00005 compared to the protons and electrons, we can usually ignore their mass with what we're doing in chemistry. I've also put in this 8-man, and that's just to remind you that atomic number is protons and electrons, represents both, although technically it's defined as the number of protons. And man stands for mass minus atomic number, gives you your neutrons. So isotopes. Isotopes are atoms of the same element with different mass numbers and therefore different number of neutrons. So isotopes have the same chemical properties, but it will affect some physical properties such as boiling and melting. The heavier isotopes are going to be moving slower at the same temperature, since temperature or kinetic energy is 1/2 mv squared, so more mass means less velocity. But that also helps to separate isotopes of an element. It will also affect physical properties like mass, density, rate of diffusion, enthalpy of vaporization, and enthalpy of fusion. Heavier ones are going to take more energy or more time. And again, since heavier isotopes move slower at the same temperature, isotopes can be separated fairly easily into something that we call the mass spectra. Other thing to realize is it will not affect the chemical properties. So it does affect some physical properties, does not affect chemical properties. The abundance of isotopes is reflected in the average atomic mass, which is the mass given on the periodic table for each element. It's calculated as a weighted average, so you just take the percent of isotope 1 times the mass of isotope 2 and add it to the relative abundance times the mass of isotope 2, isotope 3, for however many isotopes you have for that particular element. So that's why the atomic mass on the periodic table could be a decimal, but mass number has to be a whole number since it's actually representing the number of protons and neutrons in that particular atom or isotope. Ions occur when electrons are gained or lost, and the gaining and losing or the transfer of electrons is what's responsible for chemical changes or chemical reactions. So this is really what we spend the year studying. Cations form when an atom loses electrons, and anions or negative ions form when an atom gains electrons. So this is why atomic number is defined as protons, because they won't change in a chemical reaction. But remember, protons and neutrons can change in nuclear reactions. However, in inorganic chemistry, our focus is going to be on chemical reactions and the change in electrons. The magnitude or amount of charge on an ion depends on the number of electrons gained or lost. More electrons gained or lost, greater magnitude of charge. The loss of electrons has a huge effect on the atom's property, much greater than the effect of having more neutrons or being an isotope. For example, most of our nutrient elements, we need a lot of metals in our body, but we don't take them in their metallic form. Sodium, really important for most of our daily functions for the cells in our body. It's commonly ingested as sodium ion with sodium chloride or some other salt, but sodium metal would be very dangerous. It's dangerously reactive and not something we want in our bodies. So ions are hugely important within our bodies and most of our day-to-day lives. Some uses of isotopes, if you want to pause here and look at, these are probably 3 of the most common isotopes used in our day-to-day lives. Carbon-14 for dating things, cobalt-60 used in a lot of radiation or radiotherapy, and iodine-131 used as a tracer. Relative atomic mass is abbreviated AR. The little R subscript just means relative. And the mass spectrometer has been developed. It can measure the actual mass of individual atoms. And so from this, we know one hydrogen atom is only 1.67 times 10 to the minus 24th grams. And one carbon atom is just 1.99 times 10 to the minus 23rd grams. And in fact, all elements have an atomic mass in the range of 10 to the minus 24th to 10 to the minus 22nd. which makes for really little, really hideous numbers to work with. So it makes sense to use a relative atomic mass, or a mass given in AMU, atomic mass units. So atomic mass units are based off a standard. Relative means compared to something, and the standard, or what we're comparing all atoms to, is one atom of the carbon-12 isotope. And carbon-12 isotope is assigned a mass of 12 with its 6 protons and 6 neutrons. Mass spectra is just the analysis by a mass spectrometer, and it's presented in this chart where you have the relative abundance compared to the mass. Down here on the bottom it should say mass here. And so you can estimate the relative atomic mass using the spectra here. So isotope 90 seems to be somewhere around 50 to 55%. You could estimate that. And then you've got 91 way down here, with between 5 and 10%, and the 92. So you could use this information to set up that average atomic mass equation, taking your percent times your mass, and coming up with average atomic mass for this particular element. And in fact, you could identify the element with this.